Okay, we have many wonderful talk about massive black hole binaries, and dynamics of these guys. What I want to do in this talk is to give you some numbers. Okay, so putting all these ingredients in a cosmological framework, which event rate we might expect for these massive black hole binaries, and so which detection rate we might expect for LISA, basically. So I will start introducing the general framework for massive black hole binary assembly, and I will address, according to this framework, a couple of questions. First of all, the capability of LISA to probe the cosmological evolution of massive black hole binaries. So I will show you what is the impact of different massive black hole formation scenarios on LISA number counts and LISA detection. And so on the other end, we will see which is the capability of LISA to put constraint about massive black hole formation scenarios. And since we had a quite long discussion now about the kicks, I will study the impact of kicks on LISA detection, because kicks deplete massive black hole from galaxies. And so this will not only have an impact on the fraction of galaxies that show a massive black hole now, but also on galaxy or massive black hole available at each merger round for forming a binary. Okay. So if we deplete many of these massive black holes, there should be a drop into this number count you expect. So most of you should be familiar with this couple of diagrams. Here I showed, well, this is not a very recent one, but the situation has not changed too much. So we see that, so what we know is that the massive black hole mass in biology correlate with biology's properties. And we got these two wonderful relations, wonderful astrophysically speaking, between the massive black hole mass and the bulge mass, and the massive black hole mass and the velocity dispersion of the bulge. So this means that in some way this massive black hole and bulge forms together, evolve together with a common path. Okay. So what we try to do is to build a cosmological framework to evolve these massive black holes, starting from pre-galactic seed into the dark galaxies. So what you do is you assume that your supermassive black hole grown from some seed black hole. Okay, the seeds are incorporated in larger and larger halos, and they accrete gas and they interact with each other, forming binaries after each merger. Of course, building a cosmological model like this, you have many constraints to satisfy. For example, many observational constraints. The luminosity function of quasars, both in optical quasar and X-ray. The relation between the black holes and the bulges, and the formation of galactic cores, and blah 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 blah. Okay, so how we do this? So what we do a semi-analytical model. Okay. Coupled with a Monte Carlo realization of the hierarchy of the mergers. So basically what you do, you use the extended percent shatter formalism to do a Monte Carlo realization of the merger hierarchy of galactic halos. So you're starting from redshift 0. From now, you decompose the halo in the parent halos. Then at some redshift 20, more or less, you populate certain halos with seed black holes, and you trace back the evolution of these black holes, allowing them to accrete gas to the merger and so on in pairs, and then you trace back the evolution of this black hole from redshift 20 up to now. In all the models, we use the occupational fraction of the seed black holes in the pre-galactic halos, ensure that we have an occupational fraction of the hole today that is united for halos more massive 10 to the 11 solar mass that is what we observe on galaxies now. Ah, okay. Can everyone hear me?
Yeah.
Okay. You are the only one. That's your problem. So during this process, massive black hole binaries will inevitably form. Okay. With the presentation on another lap, so there will be a couple of fancy plots in this presentation. So the massive black hole binary dynamics, okay, is I don't want to spend much time on this. Lucio already talked about this. So you have during the merge, the dynamical friction bring the pair of black hole together. Then you have an Harding phase that can be driven by stellar dynamics or gas dynamics. In the model we used, we rely on stellar dynamics in a spherical system, but assuming that the loss cone is always full. So in a sense, we always have a rapid coalescence of the binary. So this is sort of toy model for coalescence of binaries. And subparticle gravitational waves takes over, and the binary coalesce. So what we want to talk is the capability of using discriminating massive black hole binary assembly models. Okay. So we have different models for seed formation. The first model that is our was our fiducial model for many years is what we call voluntary Archimedes model based on voluntary 2003 work. In this scenario, the first seed black holes are 100 solar mass black holes that are thought to be the end product of the first massive stars. Okay. And we populate mini halos at redshift 20 in 3.5 sigma peaks with such black holes. So this is a scenario in which you have abundant and low mass seeds. On the other hand, you have a completely opposite scenario in which that is the Ushap's model, in which you have very massive abundant seeds. In this model, basically you directly form massive black hole with mass 10 to the 4, 10 to the 5 solar masses due to inflow of gas in halos at high redshift. In this model, you assume that there is efficient H2 cooling, so you can form seed black holes in halos with real temperature of a few hundred Kelvin. So you end up with many seeds. And this is a upper limit for the models, because with such a huge population of seed black holes, if you follow the dynamics, you can have problem in reproducing the luminosity function of quasar, assuming a reasonable prescription for accretion during mergers. On the other hand, we have these two models proposed by Voluntary and Rees, in which you have basically a similar formation scenario, but you don't have H2 efficient cooling, but you have H cooling. And in these models, you can just form black holes in halos with real temperature that are above 10 to the 4 Kelvin. And assuming different prescription for the feedback of the accreting of the star that is accreting the material, and then the star that is supposed to form a black hole. Assuming the different prescription of the feedback of the star in the surrounding medium, you can have what we call the Begelman-Monteris high Friedman model, and the Begelman-Monteris low Friedman model. In the first model, you end up with say 10 times more seed than in the other one. The Begelman-Monteris high Friedman model is can be safely thought as a lower bound for this kind of formation models, because with such few seeds, you can barely reproduce the inoculation fraction of 1 into the galaxies. So, what you can do is, okay, put this all together put these seeds in your halo merger tree. You build up the merger hierarchy, and you end up with some coalescence rate that are shown here for the 4 different models, different colors. So, as you can see, the coalescence rate, these are a number of black holes per unit ratio per unit time per year. And so the most prolific model, not surprisingly, is the Push-Apos model that gives you something like 300 coalescence per year. And the better is high feedback model has a coalescence rate that is a couple 2 orders of magnitude lower, so 3-4 events per year. So you have a coalescence rate, and you expect those gravitational wave signal. So which is the means by which we are detecting this? Is LISA. Okay, I think that everyone of you now know everything about LISA after the talk of this morning by Vital. And so what you can do is you can compute from this merger rate the signal to noise ratio you expect as a function of I told you that there were a couple of things. So you can compute the merger, you can compute the number of events you expect to detect with LISA. And the results are shown, well, half the results are shown in this picture. So what you can see in the left panel is the rational distribution of events. And these are basically the LISA number counts you expect from these models. And for the Push-Apos model, we divided the curve by a factor of 10, otherwise it would fit in the plot. So as you can see, you expect this is assuming 3-year observation. You expect a number count of events that are between 8, 10 to few hundreds. Okay. On the other plot, maybe you can guess the mass distribution of this event. So as you can see, not surprisingly, in the voluntary automata model, that is the red curve here, you can detect black holes up down to masses of 10 to the 3 solar mass. This curve here. Of course, when you have more massive seeds, you can detect just boundaries with masses that are more than 10 to the 4 solar masses, because these are the mass of the seed. In the voluntary automata models, the mass of the seed are 100 solar masses. So this 1,000 solar masses is the lower limit that at which LISA can detect these black holes. Okay.
We can hear you, but this is a little bit difficult to see.
Okay. Anyway, so if you got a certain merger rate of these black holes, this certain merger rate is due to many sources at bigger separation that slowly spiral. So you have many black holes with a certain binary separation. So you expect to have many sources in the sky. And what you can do is to compute if these many sources that are not going to coalesce in your observation time, but that are there, okay, are going to give you some confusion noise. So if you assume a standard simplified prescription for the computation of confusion noise level as the level at which you have at least one or few sources per frequency band, you end up with curves like this for the 4 different models. So what you can see is that in any model, the confusion noise you expect is at least an order of magnitude below the LISA probability, so it should not be an issue. At least maybe he's happy about this.
Yeah, but it might be more interesting for pulsar timing.
Oh yeah, it is, but this is a meeting. So. Actually, we did a work with Beck about this. And you can see it soon on Astro page, hopefully. And we've just seen that this different seed formation scenario has an impact on LISA detection, and but in all the models we can expect, due to our current knowledge, you never end up with a 0 event for LISA. Okay, you will have at least 10 events in a 3-year mission. Okay, but there is this topic that is gravitational recoil that came out in the last year, and So we know now that highly speeding black hole can recoil to velocities that are up to 4,000 kilometers per second. And but this doesn't mean that every black hole has such high velocities. If you see this formula from Campanelli et al. 2007, you can see, you cannot see it actually here, but trust me, that the maximum recoil is achieved when the two black holes are equal mass. Okay, and in this case, this guy is 0, so you have a recoil that is perpendicular to the orthogonal to the binary orbital plane. And but what you can also see from this formula is that this recoil velocity scale with the square of the mass ratio, and Palsy, Baker et al. Was on Astro-GR a couple of days ago. There are hints that probably third power of the mass ratio is a better fit. And this case has the spin magnitude. So no one tells us that every black hole has every black hole merger is equal mass, and every black hole has a spin of 0.99999. Okay. So what we did, and there is also this cosine of this angle, which is the orientation with the spin with respect to the orbital phase, that also play a role. So it's quite an unlikely configuration, to the one for which you got these thousands kilometers per second kicks. So what we did is to put this extreme kick in these merger tree models. So basically, what we did was to trace the evolution of the spin magnitude in a consistent consistent way, yeah. And so in this model, the mergers do not preferentially spin up the mass of the population, but spread your spin distribution. But accretion tends to increase the spin. So usually at the end of this model, for massive black hole at low ratio, we end up with black holes with spin that are 0.9 or so. But what we did, we assumed that during each merger, the spins were aligned in the anti-aligned in the orbital plane. So we assumed the worst case, okay? And as Cole told us before, probably unlikely in nature. Okay? There should be no reason why nature would prefer this case. So in a sense, we are placing, at least from key point of view, a lower bound to these detections. So we run the model, we compute the sources, and this is the merger rate you end up with. So here I took two dimensional model, the voluntary automata model and the Begelman voluntary race model, the low figure. And here you can see the number of sources per unit. This is okay, even if it's a mu, this is a shear mass actually. For a unit shear mass per year, as a function of shear mass at different ratios. So what you see in this plot? In this plot you can see that the Begelman voluntary race model is very affected by this extreme peak restriction, giving you just 20% less merger of massive black hole binaries. While the situation is more critical for the case in which you have abundant light seeds. As you can see in the upper panel here, the number of coalescing binaries at low mass is more or less the same, assuming no kick, that is the dashed line, and kick, that is the solid line. But as you go to higher masses, you have a drop by a factor of 2 or 3. If you use this to compute the number of sources you expect for LISA, you see that in the Begelman voluntary race low frequency model, your number counts are lowered by 15–20%. So you still have tens of massive black hole binaries. And the situation is more dramatic in the voluntary automata model. You more than halve the number of sources because of this extreme recoil prescription, but since you, in this model, you expect many more sources, or hundreds or so, so you still end up with at least a few dozen sources. So we expect that this extreme recoil prescription at most can halve the number of detection, but still you will have at least 10 sources for Lisa, and this, I hope it's a good results for us. Why this happened? We can think about a simple interpretation of this. Thinking about the merger hierarchy as a succession of round of subsequent merger. Okay. So what you find in these merger trees is that your event rate is actually dominated by the first round of coalescences. And what happens if the seeds are right? Okay. Actually, you cannot see this first round of coalescences with Lisa. Okay. And if you have extreme kicks, starting from the second round of coalescences, you got this depletion of events. So if you cannot see the first or the first two rounds of coalescences, you're going to miss many events, assuming an extreme recoil prescription. To give you a number, in the voluntary Archimedes model, we have that 80% of the codes that undergoes a first round of coalescence experience a second round of coalescence. If you switch on this extreme recoil prescription, this distraction go down to 30%. So if you cannot see the first round of coalescence, that of course is not affected by the extreme recoil prescription, because they didn't experience any recoil yet. If you cannot see this first round of coalescences, your event rate goes down. The things are different if you start with massive seeds, with 10 to the 4, 10 to the 5 solar masses, as in the diagonal voluntaries model. In this case, you can see the first round of coalescences, so you can see the bulk of coalescence event. And moreover, since the seeds are less abundant, you have that, for example, in this model, only 40% of the black hole that experience the first round of coalescences are going to experience the second one. And this fraction goes down to 25% if you switch on this extreme recoil prescription. So the drop in the event rate is milder, also because you're getting with more massive black hole that are very low massive levels and the escape space design. On a related note, this picture is from this cartoon is from Schnittmann, 2007. Schnittmann computed also the fraction of galaxies. Very nice. The fraction of galaxies you expect lost a black hole now, assuming a certain probability of ejected black hole during the merger. And quite not surprisingly, actually, you find that assuming this subsequent round picture, you find that the fraction of galaxies after a few rounds of coalescences in which you have a black hole is 1/1 plus the probability of ejection. So, still, if you have a 90% probability of eject a black hole during the merger, still you will have a threshold 0 now. 0.6 galaxies, not 0.6 galaxies lost in the massive. So, these are in summary. So we see that we can trace by means of Monte Carlo realization of the merger hierarchy, the evolution of massive black hole binaries, and current fabric models for seed production, seed black hole production, predict for Lisa an event rate that is between 10 and a few 100,000 detection, assuming 3-year observation. This calculation is 3-year observation. And so Lisa, we will be able to probe this information. The confusion noise expected from these massive local binaries will not be an issue for Lisa, because it's well below the sensitivity threshold. And also, this extreme recoil topic will not be a serious issue for Lisa detection, in the sense that even assuming that the extreme recoil exists, you can at least have more or less the number of laser detection, but all the models we have still predict at least 10 detection in 3D vision. And